Our next speaker is Anders Sornborger from Los Alamos National Labs.
Thank you. So at this point, we're going to go from large scale to small scale. So I'll be talking about a mechanism for copying synapses between two pieces of a neural circuit or two neural circuits, depending on how you think about it. And it's going to be a pulse-gated mechanism. Okay, and this work has been done in collaboration. This is kind of Project N of a collaboration with Louis Tao. And these are some of the usual suspects. Okay, so in terms of copying synapses, I think there are kind of two main motivations to this work. One is on the neuroscience side. So Henry Molaison had bilateral lesions in his hippocampus, and he was still able to access long-term memories. He was not able to, and he was able to form short-term memories, but he was not able to turn the short-term memories into long-term memories. And so this led to people suspecting that short-term memories were learned one place, in particular the hippocampus, but then that they were transferred elsewhere for long-term storage into the cortex, in particular the prefrontal cortex, but that somehow the lesions had cut the connections that made that possible. So, and then, of course, that started a huge amount of experimental work, and recently it seems that there are nested oscillations involving the thalamus, the hippocampus, and the cortex that act like a communication channel that facilitates this memory consolidation from the hippocampus to the prefrontal cortex. So the other motivation, which I think is probably obvious to everybody, is that in a neuromorphic circuit, if you've learned something in one place, it might be useful to put it somewhere else to avoid communication bottlenecks and so forth. Okay, so this talk is going to be a talk about pulse gating and integrating pulse gating with Hebbian learning in order to perform this synaptic copy. And in order to talk about the mechanisms that we use for pulse gating, I'm going to first talk about Synfire chains, which are going to be a straw man that I'm going to knock down, and then I'm going to talk about something that we call Synfire-gated Synfire chains, which are capable of of propagating graded information. Then I'll talk about how to compute with them, to kind of implement some algorithms with them, and in particular, I'll talk about implementing an algorithm for learning and predicting an AR process, which is just a linear time series. And then at that point, we'll have all of the kind of sub-mechanisms that we need in order to understand how to do a synaptic copy. So a Synfire chain, these have been around for a long time. Abelese first published on these in 1982. And it's a straightforward mechanism to think about. It's feed-forward network of neurons. And you put in, as long as the synaptic coupling is large enough, you put in a volley of action potentials, and it goes from layer to layer through the network. And it was thought for some time that that would be the thing that the brain used to communicate information from one place to another. The problem is that we know from experiments like from Hubel and Wiesel and the visual cortex and many other places that the brain deals in graded information. Firing rates are important, so the amplitude of a firing rate is something that has meaning. For a Synfire chain, what happens is if you think of the envelope of the Synfire chain as having an amplitude, which here is the y-axis, and a standard deviation, which is the x-axis. What happens is you put in a volley of action potentials very rapidly. That pulse goes to a fixed amplitude, fixed standard deviation. And so what that means is that, yes, you can transfer information with a Synfire chain, but you can transfer one bit of information. Okay? And that's not sufficient for what we know about the brain. So Louis and I needed to propagate some graded information. And this was the modification to Synfire chains that we came up with that allowed us to do that. It's very straightforward. What you do is you put together two Synfire chains. One of them generates pulses. They're sub-threshold. And so so I wish I had a pointer. The bottom, these pulses here, we'll call the gating chain. Those are populations of neurons which are coupled to these upper populations. Thank you very much. So this is what I'll call the gating chain. This is what I'll call the graded chain. This chain provides pulses which synapse on these populations. They cause a subthreshold increase in the current. But if there's information coming into these populations from elsewhere, that'll push these populations over threshold, and then they'll fire. They'll fire downstream, and as long as there's another gating pulse here, they'll continue to go downstream. So what we did in order to implement this in an integrate and fire network was to use a standard Synfire chain for the gating chain, the pulse gating mechanism. So the standard Synfire chain sucks for propagating graded information, but it's great for generating pulses. So what we did was we generated pulses with that chain, and then with the coupled chain, we were able to propagate graded information from through many layers. Okay, so we actually spent a fair amount of time then reducing that integrate and fire network down to a mean field model. And this is just because if you want to start thinking about implementing algorithms with this sort of a mechanism, it gets expensive to do it in neurons. So this is the mean field model implementation, and up here are variables associated with the graded chain. Down here is the gating chain. Here in cyan are currents, and when this gating pulse it couples to the graded chain, it pushes these currents which aren't inducing firing, and here in yellow I show the firing. So the gating causes the currents to be transformed into firing rates. The firing rates propagate downstream, or the spikes propagate downstream and are integrated by a downstream population. And if you had another pulse on the downstream population, it would propagate as well. Okay, so the main implications of having this kind of a mechanism is that because you have these two chains, the gating chain and the graded chain, what you've done is you separated out the control of the propagation of information from the information content. And that's crucial because this control can be very precise, and you can get information in your circuit exactly where you want it, when you want it. And so with this Synfire-gated Synfire chain, we can use it as a building block and start constructing neural circuits that implement algorithms. So the last thing that you need to know about computing with these things is with the Synfire-gated Synfire chain, is that, of course, so far I've just talked about taking information from a average firing rate from some population and faithfully propagating it to another population. But you can generalize the mean field model, and in fact the integrate and fire model, to have a vector of populations talking via a synaptic connectivity matrix to another vector of populations. And so here's our connectivity matrix. And then the pulse gating, which now gets generalized to a vector of pulses, allows you to dynamically route information through your system. So you have the kind of concept of pulse-gated or actively gated linear maps, where you can, using the pulses, you can instantiate a linear map and also determine downstream flow of the information through the circuit. Okay, so we were interested in understanding how this kind of pulse gating could be used in a learning context. And so the first thing that we thought we would do would be to take the standard linear process. This is an autoregressive process. An autoregressive process is driven by noise, and the current value is a convolution of some set of previous values that are a convolution with those and a set of coefficients which define the process in order to get the next value. So in order to learn in this kind of process and make predictions, we have to estimate the covariance matrix of the process. So this is a covariance between all the lagged values, some recent set of lagged values of the process. And then we use the coefficients, we use the covariance in order to estimate process coefficients. And then we do this, predict future process values by convolving over the coefficients and the previous values of the time series. So in order to do this, in order to implement these three subcircuits, I'll show you them one by one. Here we have a circuit which learns a covariance. So how does it work? We have a time series that comes in, and it goes into a short-term memory. So we use pulse gating to take this value, gate it into the circuit, and then gate it to successively later memory populations. You can see that this is split into positive and negative components. That's just because it's a linear process and we need both positive and negative values. So it's kind of just a technical consideration. But now and then the white lines here indicate fixed synapses, and the cyan lines indicate Hebbian synapses. The Hebbian synapses are feed forward, but the Hebbian synapses only work when there's simultaneous firing on both sides of them. So what we do is we take the process and we gate it to both sides of these synapses at the same time. So these guys go here, and same with all the rest. And then the Hebbian synapses, where the weights are proportional to the product of the input and output, then learn the covariance of this process. The next thing that we do is we need to do gradient descent in order to estimate the process coefficients. So these P's are combined vector of the positive and negative parts of the coefficients. And this is just a discretization of a gradient descent algorithm. And this circuit here represents the steps that you need in order to implement this iteratively. So the thing to notice here is that now, instead of writing to both sides of the Hebbian synapses in order to induce learning, we gate the information from one side to the other side. And because of the precision of the pulse gating, when we gate it through, there's never an overlap between the input and the output. And so this gating doesn't change the covariance matrix. Then the last thing that we need to do is to form a dot product, which is to take the sum of these products of the coefficients. So it's not called P now, it's called A plus, because this is a positive coefficient, this is a negative coefficient. But we take and we form these products, and then we need to sum them together. But in this simple framework, we don't have any obvious way of doing this multiplication. So what we did, and this is going to be important for the synaptic copy, is we started out the circuit so these are Hebbian synapses, and we write a unit value or some canonical fixed value into these left-hand populations, and in the right hand we write the coefficients coming from the previous circuit that I just showed, and we write them at the same time, so Hebbian learning turns on, and the covariance between these values is the value of this itself. So we burn the process coefficients into these Hebbian synapses, And then later we can use this by writing the time series into this side, gating it through these synapses, forming these products, and then summing them up and getting the prediction. So the way this works in terms of looking at how the pulses guide the information through the system, we have the short-term memory. So down here, these will be different neuronal populations, and then this will be time. And this pulse sequence will be repeated iteratively and will converge to the correct covariance and coefficients and predictions. And so here, this box shows you, this is the gradient descent, the pulses that guide information through the gradient descent circuit. You can see that it uses part of the covariance matrix. Then here is a pulse sequence that is learning the covariance. It guides information, the graded input through the short-term memories, and then gates it to both sides of the Hebbian synapses and learns the covariance. This is some other short-term memory that's used to keep information around. And down here is the coefficient learning and prediction pulse sequence. And you can see that these are all separated. You wouldn't want to have the gradient descent circuit interact with the covariance learning circuit because things would go horribly wrong. On the bottom is just showing the graded information. So this is the Synfire chain that's pulsing everything through. And then this is the graded information as it gets propagated through the network. And this input here, which is in the short-term memory, is determining what covariance gets learned. And you can see here, these are the covariance matrix elements. They converge on a time scale, which is proportional to the Hebbian learning time scale. And then here, the process coefficients. Initially, they go horribly wrong because the covariance is all wrong, but then they settle down to the correct values. Okay, so now we've got all the mechanisms that we need in order to copy synapses. And there's one conceptual addition which I'll point out. So here's a synaptic copy circuit. We have, again, short-term memory circuit, and then the input and output to some Hebbian synapses, which I'm showing in gray now. The white synapses, again, are fixed synapses. Input and output to Hebbian synapses. And then this is the part of the circuit which will be for copying a covariance matrix or synapses from here to here. And then this part is, remember I was using this mechanism of writing a 1 somewhere and on one side of a Hebbian synapse and then writing something else and then burning information into the system. This is doing the same thing, only we need to do something a little bit more complicated. Okay, so the pulse sequence to copy from one to the other looks like this. So initially, we just run this part of the algorithm. This takes information, reads it into short-term memory, and then that information is gated simultaneously to the input and output sides of the covariance matrix. So this simple pulse sequence will learn the covariance of the time series in these synapses. And then if we write a unit value in here, these pulses are a memory to save that unit value. And then here's the crux. So what we do is we have the covariance matrix that we learned. We turn on this part of the circuit later on. And we write a Euclidean vector. This is a 1, 0, 0, 0. So it's an axis vector in 4 dimensions. And we gate it through the covariance matrix, and that gives us the transformed Euclidean vector. We write the next Euclidean basis vector in, and then here and here. And then we arrange it via pulse gating to delay this through a short-term memory and write this down here and to the far side of the synapses that we want to copy to. And because this and this are being written at the same time to both sides of that matrix, we then the matrix, due to the Hebbian learning, will learn that covariance. Okay, and I should say that this is effectively a Green's function type technique. It's quite simple from the linear algebra point of view. We're just generating transforms of these Euclidean basis vectors. So if we look, this is the connectivity matrix, and just focus here. So initially, like I said, we just turn on the covariance learning part of the circuit, and this is the covariance matrix that's learned. Later on, we turn on the copy, and this is the initial covariance matrix, and then after the copy, we get this. Okay, so the main point here, or the first main point, is that we can use pulse gating to very precisely control where information is in a neural circuit. And we implemented a circuit capable of first learning a stochastic process and then transferring that process, not the process, but the synapses that we learned, the covariance matrix, to a secondary circuit. Second thing is that this transfer circuit makes use, because it's, the pulse sequence that we have is done over and over again, it makes use of nested oscillations, which is the epiphenomenon of memory consolidation from the hippocampus to the cortex. And it operates independently of the process that was used to learn the synapses in the first place, which is something that has to be true for the brain, because if you're going to copy the synapses might be learned from some input or whatever, but then when you copy them, you no longer have that process available. And then the final thing to say is that there's a long-standing problem implementing gradient descent and in neural systems, and the problem is what's called the weight transfer problem, which was pointed out by Grossberg and Crick early on, and this circuit, the existence of this capability solves that problem. So thank you. Any questions?
So I have a real quick question while Hava's setting up. So how many, I don't know if you said it, but exactly how many neurons do you need to do this copy? Like, what is the sort of scaling efficiency of this replication process?
Yeah, so that's a good question. So in the integrate and fire simulations that we did, which don't implement this kind of a circuit, it typically, for the Synfire chain part, the pulse gating, we're using about 100 neurons per population and about 1,000 for the graded information. If you didn't want very high resolution for the graded information, you could use less, but that's about it. So, yeah. Okay.
Let's thank Andrew again.